Hello everybody, welcome to another problem session. Actually, this is a concept session. This is second in I don't know how many parts will take me to build up foundation for the vector vector way of looking at rotation. So we've talked about this in the last video. So if you haven't looked at the last video, go ahead and look at it. So just very briefly, what we're going to do is it's going to be rotation and you can see these are concepts like rotational velocity. We're going to look at the vector and then angular momentum. Today we're going to look at momentum, and then we'll also look at moment of inertia, and maybe if you get a chance we're going to look at maybe I will just briefly mention principal axis, and then later on we can talk about kinetic energy of rotation, and then after that we can go back and actually do some problem trying to find out principal axis. Okay, so that's like a roadmap. After we have developed those things, we will be in a good position to talk about precession and how the axis of rotation is not fixed, but itself can be rotating, for instance. Okay, so let's look. That's our roadmap. So I think yesterday I did this video and talked about a rotational velocity. So you're familiar with writing. Let me just. Today I have really a big setup here. So I have lots of space here. All right. So over here, let's do black. So you have V equals to omega r. You have this formula from before when things go in a circle. Omega is the angular velocity, and r is the distance from the center of center of the circle. So this has gone into velocity vector equals to cross product, and this is now position vector. So this is completely whether something rotating or not, you can use it. So say something is going in circle, just for illustration, but it doesn't have to be circle. But so we talked about like this guy is going in a circle, and this is a point mass m, and this is the origin. So from here to here is vector r, and rotational velocity is pointed along the axis of the rotation. So this is going around the axis. So this is very important to notice. This omega is not pointed this way. Actually, what's pointed that way is along the circle is the V in the direction of motion. So this is what you expect, is point tangent to the motion. This is not something you expect. Okay, so the direction of this is not going circle. I mean going in a curvy way. Each one of them is straight. So this is straight, this is straight, and that's also straight. So the vector is a straight line. Okay, a straight direction arrow. That's why you use arrow. We don't say this is a vector. This is not a vector. This is not a vector representation of anything. Okay, it's a direction representation. It's going like that, but it's not vector. Vector will be like this, that. It will be straight. It will be straight like that. All right. So today we're going to do angular momentum. Let's do what is angular momentum. So if I have a point mass m, and I have So this is some origin, and didn't hit that. Let's call it R, just like over there, just like over there. And so this is a position vector. Let me write down position vector. Okay, in the position vector, and it maybe is moving in that direction, maybe. So this is some instant t. This is the situation, okay? This is the situation. So it's going that way, position R vector. So you know the momentum of this. This is the definition of momentum, mass. So this is a momentum vector, right? This momentum vector. All right, so so this is momentum vector. It is a vector quantity, and sometimes called linear momentum, or some translation momentum. So this is an alternate momentum. Okay, so this is a point mass. So this is a system of a point mass. Maybe you already realized the point mass is a building block. So you have a rigid body, then basically you can just break it up in the body into infinitesimal masses and treat them, each one of them, parts of the big object as point masses. So if you know how to do point mass, you basically sum it up, integrate whatever you do later on. But the point mass is building block. So when you're trying to figure out a concept, it's better to actually do it in a point mass. Okay, so here is a point mass. Momentum you already know, and R is the position vector, like we talked about above. So now I'm going to define. So this is actually definition. This is also definition. So I'm going to do another definition. I'm going to have an angular momentum. Whether it is rotating or not, it doesn't matter where something is rotating. When we define whether M is rotating in a circle, rotating or not. So sometimes people say something going in a circle is rotating, but that's not really our language here, okay? So it may be moving like that, and it may be V is that way, and over here R is that way, and V is that way. So it's not going in rotation or something like that. So if this mass is over here, we can still define angular momentum. This is an abstract concept. I'm not going to attach a physical meaning to it yet. So this will be, letter L is used for angular momentum normally. You would say letter A would be used, but not. And this will be a vector, will be simply R cross P. So this will give a fundamental definition of angular momentum. Now, if a system was something like this, going in a circle or has a angular velocity I can attach to it, then I would like to know what this becomes if in that case, okay? So in that case, I can use this. So I can write this as R cross M V, and I can replace V by what we have found, angular velocity times the position vector. So this is going to be R cross M omega cross R. Now, M is just a scalar, so it just comes in the front. Okay, so it just comes in the front. So let's see, M. So you have R cross and the result of omega cross R. So this is, we need to figure this out. you know. So when we are going to do a much simpler figuring out. This is completely general right now. So we want to write for a particular case. So let's look at an example. And when we do a particular case, we should make it so simple that when we see the formula, we can guess the formula in the general case. We don't have to really work out the components. So let me give you an before I give the example, let's look at this closely. So what we want from here is, what is the formula for x component? What is, so this will have x component I hat plus y component j hat plus z component k hat. So if I do the same thing over here, break it up like that, so what will this formula will be? Or the ly formula will be? Or lz formula will be? Maybe you can work it out, you know, if you feel up to the challenge, rather than do a simple problem and then work it out. You can just attack this completely by writing this as omega x I hat plus omega y j hat omega z k hat, and writing r as x I hat plus y j hat plus z k hat. You can just write it straight out like that, and then you can expand the hell out, so to say, and eventually you should get, once you expand this whole thing out, you will get some blob I hat, some another blob j hat, another blob k hat. So you're going to get different blobs, and you can say, wow, Lx is that guy over here, and Ly is this guy over here, and so that is doable, but it is not very illuminating. And so what I like to do is pick up a simple yet illustrative example, okay? As we have done in the yesterday's last video, okay? So let's look at this way. So we could do a really simple one, and it would be too simple. So suppose we do something is going xy plane, like that way. So this is x, y, z. So when you do this, what trouble is the position of this guy, the position vector here is just x I hat plus y j hat. Z is 0 all the time. And it kind of gives a too simple a formula, okay? And maybe you can work this one out and you'll see it's too simple a formula. And in the interest of time and completeness, I'm going to skip over this. And I will say it's a homework for you, and you better do it, what it look like, all right? So let me do a little kind of in between things that is kind of like this situation over here. So it's z is not 0, but it's still circle. It's still parallel to the xy plane, okay? And at some time t, so let's say this is z is a. So vector r and omega is simply omega z k hat. There's no omega x, omega y. It's all pointed along the z-axis. Okay. So this is mass m. So r is going to be x I hat plus y j hat plus a k hat, and omega will be omega z k hat. So now take what we are trying to figure out is take this cross product first, and the result of that take that with this. Okay, so that's what we're trying to do. So we're trying to do omega cross r. You can do this cross product several different ways. You can write like You can probably know this way of doing it, I hat, j hat, k hat, and write the omega z here, then 0, 0 omega z, and then x, y, and a. And you can do this determinant. Or you can do another way, is just expand this. So omega z times x, k hat cross I hat, plus omega z y, k hat cross j hat, plus omega z times a, k hat cross k hat. So now we have interesting thing. This guy will go to 0, and this guy, you probably know this. If I have I hat, j hat, and k hat, if I go this way, you get the other one with the positive sign. If you go other way, you get negative sign. So if you go from here to here, you get this guy with a negative sign. So this is going to be minus I hat. And I'm going in the same direction, so this guy is going to be positive sign with j hat. So this is just going to be omega z x j hat minus omega z y I hat. Okay, now the next one is to actually do r cross the result of that. So the result is that, just take that. So let's do it very quickly, and take a maybe this guy. So I have x I hat plus y j hat plus a k hat. So L is equals to m times cross of this guy. Let's do minus omega z y I hat plus omega z x I hat. Again, you could do using determinant way, or you can just expand it. Take one of these and go through this. This one must be j hat. This should be j hat. So if I go this one with this one, I'm going to get I hat cross I hat. I'm going to get 0. I hat cross j hat is going to get k hat. So m omega z x square k hat, and then second one, I've got j hat with I hat is going to be minus k hat. That will kill this minus sign. So m and then it's going to be y square m omega z y square, another k hat, and this with this will give me 0 because j hat. So remember, the I hat cross I hat is 0 and j hat cross j hat is 0. Now this one with that, k hat with I hat, if I go k hat with I hat, is going to positive sign, so it's going to be minus m a omega, let's say ay, the ay omega z j hat, k hat with I hat gets j hat, k hat with j hat, I'm going this direction, so it's going to minus I hat. So I'm going to get minus m a omega z x I hat. All right, so let's do a little bit of house cleaning. With I hat, it's going to minus m x a omega z I hat minus m y a omega z j hat plus m x square plus y square omega z k hat. So in this case, this is going to be Lx, and this will be Ly, and this will be Lz. So you can see that if I were to replace x with, say, a with z, so let's call this z, and y z. This would be kind of generalization if the rotation was only along the z-axis. So this I'm going to write down. I've got Lx. I'll write down I x z, this part. I'm going to write like this, and omega z I hat plus this part I'm going to write is I to subscript y z omega z j hat, and this thing will be I z z omega z k hat. Pretty cool, right? So so we figured out if omega is omega z k hat, then L is written in this, L vector is like that, and it's not along the angular velocity direction. Remember, the p linear momentum is always along regular velocity direction, but this L is not in the same direction as omega. So this is a big distinction between what happened to the vector nature. The vector nature of angular quantities is not very simple compared to the linear things, okay? And those often people miss this initially, and they run into trouble when they're thinking problem, and then they have to go back and correct this misunderstanding they had. So this is not parallel, okay? Now only when is parallel? If this was like if we had a situation in the xy plane, then z would have been always 0. That in this case you would have said that a would have been 0, and so this would have been 0, and this would have been 0. So in this case L would have been completely m x squared plus y squared. That's the radius of this thing, and omega z k hat. So in this case, you write down I, and this just write an omega, because that's what it is. So this is just omega k hat. So in this case, you're used to writing I omega k hat. You wouldn't ignore that because because there's only one direction that's kind of relevant. But here, you get corruption from other directions as well, you know. So you can see right here tells you this is the moment of inertia for point particle mr square. So what we have discovered by doing this simple algebra is that you have generalized this sense of moment of inertia. So even if the rotation was along the z direction only, you have a moment inertia along the x direction and the y direction. I mean, there's somehow x and y are affected, angular momentum in x and y direction are affected by it. So let's do a little bit of house cleaning here. So you can write Lx, Ly, Lz is this notation of matrices where you put down components as a column vector. So this is like a column matrix. So you represent Lx, Ly, and Lz as column matrix, and then you can say what we have is first index will be correspond to those guys, xx, I, xy, I, xz, and you can see how I'm going to do yx, I, yy, I, yz, I, zx, I, zy, I, zz. So this 3 by 3 matrix, so 3 by 3, and this is 3 by 1 column, 3 rows. This is the number of rows and number of columns, and you have a matrix multiplication. So if you know matrix multiplication, then you can see that these guys will come down like that. And so this will multiply with that, this will multiply with that, this will multiply with that. So this is going to be I, xx, omega x. So this second index usually goes with that. I, xy, omega y, second again. So this is going to be I, xz, omega z. Then this guy will come down like that. I'm in the y row, so y x omega x plus I y omega y plus I. These are indices. This is not a y coordinate. Okay, so make sure you don't get confused with x and y. I zx omega x plus I zy omega y plus I zz omega z. So now we can say Lx is this guys. So if omega x is 0 and omega y is 0, which was the case in our example, you can immediately see that you have I x z omega z. So that's the case over here. I y z omega z, that's the case over here. I z z omega z. Okay, so we also found out that the formulas for these over here. So we found out I x z was minus m x z. I y z was minus m y z, and I z z was m x square plus y square. Great, right? Now, because we did a special case, you can see from the pattern here what the other guys will be. We have these guys we figured out. And of course, you can figure out those other guys very similarly. I bet I'll give you a couple of minutes. You can pause it and see if you can guess it. So this will be like I. If I do, instead of z, these guys are all y. So let's go do that. X, y will be minus m x, y. Just replace the z because there's nothing special about that, right? I, y, y will be m. So this will be more like that because both indices are same. So it's going to be, instead of y, the z had x and y. Now the y will have x squared plus y, z squared. And I z, the last one, zy, will be minus m z times y. And you can similarly get that thing, similarly will be, you can obtain that. I'm not going to write that down. You should write that down, okay? Now it's all getting very complicated. You can see that I getting over here. This is a very simple rotation. I had chosen the XY coordinate down here, and I got all kind of messed up, right? What if I had chosen, if I go back here, it says, no, what's the point in choosing coordinate system, right? Oh, let's choose origin over here and work with this coordinate system, okay? And keep the z prime in the same direction. Now you choose that coordinate system, then these guys go away. So choosing a coordinate system kind of simplifies it, right? So over here you had this, and for this, writing this collection of things, we can call that just I, big I. Sometimes people use a bold I or something like that, just to represent these 9 things. This thing looked like I have a everything. This gave me this guy I YZ non-zero, I XZ non-zero, IZZ non-zero. So all those three things were non-zero. The other things don't matter, right? Because they didn't even figure into it, and I don't want to calculate them. All right. But had I chosen in this scenario, so inside I, you have these guys non-zero. So just those guys. So non-zero, 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 and the rest of them, we're not going to say anything about rest of them. Okay, just looking at that. So let's see, I choose this as a coordinate system. X prime, Y prime, Z prime. In this coordinate system, XZ will be 0, YZ will be 0, and IZZ will not be 0. So this complicated moment of inertia is turned into, like, forget about those guys, we're not talking about those guys yet. So you have 6 of these, we're not looking at it, but these guys become 0, 0, and this become non-zero. So by choosing coordinate system properly, you can actually kill all the off diagonal. So this is the diagonal part, and these guys are off diagonal, and this is the diagonal part. So by choosing properly, you can actually kill off the off diagonal parts, and you're only left with the diagonal parts. And usually it's a very symmetric axis. So they are called principal axis. So given any system of masses or bodies, there are some directions. If you choose X, Y, and Z and put origin in appropriate places, then you will end up with you will end up with only the entire moment of inertia thing. Rather than 9 of them, it's going to get a 1 of this and 0, 0, and just the diagonal elements will be non-zero. And we can write them 1, 2, 3 or X, Y, Z, whatever. But this will be the only non-zeros, and sometimes 2 of them will be non-zero, and third will be 0. So that will actually be a So here is an example of principal axis. Suppose I have a rod, and then I say, okay, I better choose coordinate axis like this. So rotation about this, rotation about this, and the third one, rotation about that. So say this is x and y and z. So about this, all the masses are so close to the axis. So this, for this guy, you will have about x is going to be 1/12, and say this whole thing is m and l. Those are the values, m, l square. You have to work it out. I haven't worked them out, but when you work for the whole rod and you choose principal axis like this, you get this 0, 0, but along the y it will be 0, and along this particular z will be 1/12 ml square. So you can see, but if you choose, say you were so crazy, you say, I don't want this, I don't like this axis. I want to choose a different axis system. Maybe you want to have this way, okay? Have x, y, and z, okay? So y will still be 0, but you will have a different system here, okay? And if you got even more crazy, you say, I don't like any of those things, and I want to choose this coordinate system, some distance a from there, okay? So this, all of this is z equals to a. You get yet another moment inertia tensor. So choosing an axis is a very important game, okay? You probably know about cylinder of, say, radius r, length l. It will have moment of inertia. Principal axis will be, symmetry axis. Just that will be one of the axes. Another axis will be that right go through the center. So this will be axis 1, 2, and 3. And you can use these coordinates, and you get a diagonal moment of inertia. Okay, and so often we're just interested in a rotation around this. Then we just need I2. If I want rotation around this, I need I3. I don't need all of that. So in that case, L just becomes maybe I1 of this guy, I omega. And that's why whenever we do problems with fixed axis, problems like this, we only deal with principal axis. And when we're looking at problems, we're going to definitely be very much focused on principal axis only. Okay, so that's all for momentum inertia and angular momentum vector. Next, we're going to actually talk about kinetic energy, how the kinetic energy the formula of kinetic energy. So if you remember, kinetic energy of rotation is half I omega square. Now we know I has like 9 places I can come from. Then what's that I? Okay, which I will play, and it turns out this is very, very much more complicated than it looks. It looks like, so you have a omega x, omega y, omega z. So this is like a row vector, and then this i's, those I guys, I xx, I xy, this whole thing, I z z, this whole thing, and then you have omega x, omega y, omega z. So you can do a matrix multiplication, and you can get the total kinetic energy rotation. This whole thing is written is like omega vector vector. Sometimes people write it like this, and sometimes people say, okay, put this transpose here, because if you're going to use this for column vector, then the row vector has to be transposed. Sometimes people write like that. We're not going to have much occasion for writing. Sometimes people just write like half big I and omega square, and everything is bolded, meaning things may be more complicated than what they look. And this is just a so-called symbolic way to writing it. But if you are dealing with a really complicated situation, you'll have to work this whole thing out. Okay? I will do how this becomes this way, how this generates this in the next video. For now, that's all. Okay, take care. Bye.